Having looked at center of mass problems for one-dimensional discrete systems and two-dimensional discrete systems, the next thing I want to look at is the situation where I have a region of the plane and I want to calculate the center of mass of it. To begin with, we'll have a region that starts at x equal a, ends at x equal b. The top of the region is described by the graph of y equal f of x, and the bottom by y equal g of x. In addition to the fact that I have many more points than I did previously, we're going to have an additional complication. We're going to think about the situation where the mass density, the amount of mass per square meter of material here, may vary from position to position. Depending on your location within the region, you'll have a mass density of rho, which will depend on both x and y. It's important to understand here that unlike what we're used to, here y in this context is not a function of x. It's just a number that tells me the location in the up and down direction within my region. In this row of x and y, the x and y are considered to be two completely independent variables. As usual, I'm going to divide the range of x values up into smaller subintervals, and I'm going to think about what happens with one of them. So I'm going to pick one of these to look at. Its horizontal width is delta x number I. In the end, that'll end up tending to 0. Within that subinterval of x numbers, I'll pick a representative x number, which for convenience, I'm just going to call x number I. Previously, we've called that c number I, but as we're about to see in a little bit, I'm going to have more than one kind of representative numbers running around. So for emphasis, I'm actually just going to call it x number I. What I'm going to want to do is to figure out the contribution to the mass, the moment about the y-axis, and the moment about the x-axis due to this one particular strip, which I've drawn in as magnified. Got to emphasize, when I'm looking at this one particular strip, the xi is a constant, the delta xi is a constant, and to move around in my vertical strip, it's going to be the vertical motion. Eventually, the delta xi's tend to 0, so there will be no horizontal wiggle room at all. That means that I can represent the location of this vertical strip in terms of how far out it is from the y-axis by a single number. I'll just use the number xi here. Obviously, that's not true for the y numbers. Just because I'm going to let the delta x tend to 0 eventually, that doesn't mean that the graph of f and the graph of g come together at that location. In fact, generally speaking, they don't. I can characterize the horizontal location of this strip with a single number, xi, but I can't do that for the y-coordinate. The y-coordinate varies, so naturally what we're going to do is the same thing we always do. We're going to chop the range of y numbers, which starts at g of xi and ends at f of xi, up into a whole bunch of little bitty pieces, and we'll look at a piece. I'm going to call the vertical height of the one piece that I'm going to look at delta y number j. I'm going to make this piece very small so that I can more or less identify its location with the single y number in the vertical direction, but obviously a y number that would be good here is not a y number that would be good here. So I'm going to have several of these things. As I move around on the vertical strip, it's going to be convenient for me to always use the same x-coordinate, but I'll have to pick a different y-coordinate for each little rectangular block. Since I'm calling the vertical height delta y number j, I'll call the actual y-coordinate y number j. In order to analyze what happens with vertical strip number I, I'm going to chop vertical strip number I up into smaller pieces. Then I'll add up the contributions that come from those pieces and take a limit. That will tell me the contribution of chunk number I. Then I've got to add up all of those and take another limit. So this process is going to be considerably more complicated than what we're used to. If we make the delta x's and delta y's small enough, the mass density won't have much opportunity to change over this one little rectangle. That means I can represent the mass density for the rectangle by using my representative point. The mass that goes with this one little rectangle is going to be the mass density evaluated at xi and yj times the area of the little rectangle. Area of a rectangle, though, is easy. It'll just be delta xi times delta yj. So the first of three quantities of interest, I'm going to take the mass density, I'm going to multiply it by delta xi delta yj. That'll be the contribution to the mass from this one little rectangle, which is a subchunk of vertical strip number I. On the other hand, if I want the contribution to the moment about the y-axis, I've got to take the mass of the chunk that I'm looking at and multiply it by a number that represents how far out from the y-axis I am. And as we said before, the x-coordinate is the measure of how far out from the y-axis you are, either in the positive or negative direction. To get the chunk of moment about the y-axis, I just need to take this previous thing, the mass, and multiply it by the x-coordinate xi. I also need to know the contribution to the moment about the x-axis, but that works the same way. I've got to take the mass, which I already know, and multiply it by a number that tells me how far out from the x-axis I am. That would be the y-coordinate that I'm using to represent the block, which is y number j. And I want to emphasize again that if I'm just thinking about vertical strip number I, then the I is a constant, xi is a constant, delta xi is a constant, and as I move around on the strip, that corresponds to changing the index value of j. The yj's are not constants, and the delta yj's need not be constants. To find the contributions to each one of these things for the vertical strip number I have to add up each one of these quantities over index j. I is a constant when I'm thinking about chunk number I. If I add up all of the rectangular blocks that goes with vertical strip number I, my approximation for the mass of chunk I is going to be the sum over j of the mass density at xi times delta xi times delta yj. The approximation to the moment about the y-axis is the same sum, except it has an extra factor of x number I, and the moment about the x-axis is the same sum except its extra factor is yj. In each one of these sums, there are some quantities that are constant in terms of the current context, looking at strip number I, while others, anything that has index j, is not a constant. So we'll factor out stuff that's constants. In the mass, I can just factor out delta x number I. In the m sub y, I can factor out an xi and delta x number I. And in m sub x, I can factor out the delta x number I. In that last one, I cannot factor out yj because j is an index of summation here. You have to look at this the right way. In this context, xi is a constant. Delta xi is a constant. The variable is y. I've got delta yj's. So if I allow the delta y's to all tend to 0, the things inside the brackets are going to turn into integrals with respect to y. The xi will still appear, but within the current context, xi is a constant, so I'll just write the xi down again. When I take the limit as all of the delta y's tend to 0, though, the yj's turn into y's, as we've seen before. So this is going to be the integral of the mass density evaluated at x number I and y, integrated with respect to y. If you'll go back and look at the diagram, within chunk number I, we know the smallest and biggest values that the y-coordinate can take on. In this context, xi is a constant, so g of xi and f of xi are constants in this context. The two moments are exactly the same thing, except they have extra factors put in. When you do a definite integral, the variable of integration doesn't show up in the answer. So despite appearances, here say, despite appearances, that doesn't actually have any y in it. It has xi in it. It has g of xi and f of xi, but there are no variables y in that. I need to elaborate on that a little bit because it's an important point. If somebody asked me, does that integral depend on x? My knee-jerk response, if I don't think about it very much, is to say, well, sure it does. It has an x in it, but that's wrong. The answer is 1. The integral from 0 to 1, 2x with respect to x is 1. There's no x in 1. The same thing would happen if I used some other letter for the variable of integration. It doesn't matter what symbol you use. The integral from 0 to 1 of 2 times variable with respect to variable is 1 no matter what, and x doesn't show up in the answer, or z, or this capital Greek letter whose name I've forgotten, or smiley face. It makes no difference. So returning to these three formulas we have here, as I was saying, despite appearances, none of those things inside the brackets actually depend on y. They do depend on x number I, but they don't depend on y. If I were to add up the contributions that correspond to the different I values now, this would be a sum over I of quantities that might be simple or might be monstrously complicated, but they have x number I in them, multiplied by delta x number I. If I take the limit of that sum as all of the delta xi's tend to 0, this is the definition of an integral. Previously, we've expressed the thing in the box as f of ci, or in this case, f of xi. Here, maybe it is just some f of xi. Maybe it's just some monstrously ugly thing that has x number I in it. It doesn't make any difference. I'm going to do the same thing either way. The limit of the sum turns into an integral sign. The delta xi's turn into dx, and no matter what the stuff that had x number I in it was, I write down that same stuff, except instead of using the representative x value, I just say the name of the variable x in this case. Following that idea, if I take all of the chunks of contributions to the mass, add them all up, sum them up over index I, and take the limit as all of the delta x's tend to 0, the mass turns out to be an integral. It's the integral of whatever's in this square bracket with xi replaced with the letter x. At first glance, this result looks completely crazy, but you have to remember the context. When I'm doing the integral inside the brackets, I regard the x as being a constant. That means g of x will be regarded as a constant, f of x will be regarded as a constant. For the inside integral, the one in the brackets, y is the only variable. When you do that definite integral with respect to y doesn't appear in the answer, so it's just some expression that involves x then. So you're going to be doing the integral from a to b of something that only has x in it with respect to x, and that turns into a regular old calculus 1 integral. If you look at the chunk of the moment about the y-axis, I'm going to take expressions that look like x number I times something that only depends on x number I, the thing inside the bracket doesn't depend on y, multiplied by delta x number I, add those up and take the limit as all of the delta xi's tend to 0, and that turns into an integral as well. And lastly, if I look at the moment about the x-axis, I'm going to add up the contributions over index I, take the limit as all of the delta x's tend to 0, and I find out that the moment about the x-axis of my entire region is this. And not to repeat myself too many times, these integrals are not as bad as they look, because when you do the ones inside the brackets, you treat the x as a constant and y as the only variable. So in the back of your head, when you see the x in the inside integral, just pretend that it's a constant value of 3 or something. Think to yourself, constant factors in an integral are easy to deal with. Now that we know the mass, the moment about the y-axis, and the moment about the x-axis, it's easy to figure out the center of mass. This page summarizes everything we've figured out about these variable density center of mass problems. I want to work an example of this, and then I want to investigate the simple case where the mass density is a constant. That will make some of these integrals a lot easier to do, and what I want to see is, I want to see that this reduces down into the simple formulas that are found in the textbook in Chapter 7. Since I don't want this video to go on too long, I'm going to split this up into chunks. We've set up the way we do our integrals in this first chunk. Next, we'll do a variable density problem, and then after that, we'll show that in the case of a constant density, our ideas reduce down into the stereotypical formulas that are in your textbook. I hope everybody's having a good day. I'll talk to you again soon.